All right, everybody. I think we're going to go ahead and get started with the last few talks of the morning session here. The next talk is going to be by Danielle Moser, who is part of the Meteoroid Environment Office at Marshall Space Flight Center. And Danielle, I hope you're back from break. And if you are, we're ready for you whenever you are.
All right, can you hear me?
We can, loud and clear. Thank you very much.
All right. My name is Danielle Moser, and I'll be presenting for Rob Suggs and talking about a large meteoroid impact on the moon we detected on the 17th of March earlier this year. So to get some organizational details out of the way, first I'll tell you a little bit about our observing program and then get into the details of the meteoroid impact. So in early 2006, we began an observing program to monitor the moon for impact flashes produced by meteoroids striking the lunar surface. And so we observed the unilluminated or earthshine portion of the moon with two 0.35 meter telescopes simultaneously. And these telescopes are outfitted with black and white CCD video cameras. The interleaved 30 frame per second video is digitized and recorded straight to hard drive, and then that video is analyzed with custom software. So you can see in this graphic on the left our observatory at the Marshall Space Flight Center. On the right is an image of our field of view. And our field of view covers approximately 20 arc minutes. And this corresponds to a lunar surface area of 4 times 10 to the 6 square kilometers, either on the leading or trailing edge of the moon, depending on the lunar phase. So we observe when the illumination of the lunar disk is between 10 and 50%, and that yields a maximum of 10 observing nights per month. So in the last 7 years, we've observed over 300 lunar impacts. And for more information on this ensemble of data, I'll refer you to these publications over in the right corner that we've published in the last couple of years, and then I'll alert you to another one that should be out later this year, hopefully. So 300 impacts in 7 years. Now, plotted up here, I have kind of a raw number of fireballs, those are bright meteors, detected by the NASA All-Sky Fireball Network. So that's plotted in black. And that's shown alongside a number of impact flashes in pink. So that's plotted up versus time, essentially. And I'm showing you meteor shower activity as indicated by a 3-letter meteor shower code. So these two methods of observation see meteoroids in a similar size range. Preliminary analyses indicate that most impact flashes are associated with a particular meteor shower as opposed to the sporadic background component. So like I said, we've seen 300 impacts, and here are 4 examples. So for each of the examples, you see our field of view, and then our impact flash is boxed in white. And then below that, you see kind of a film strip, and this is the impact flash in time, so the intensity in time. And then for each example, I'm also showing the date and time of the observation, the duration, the peak R magnitude, the impact or mass, and the meteor shower association. So these 4 examples are associated with the Geminid, Leonid, South Taurid, and Lyrid meteor showers. Now, typical impact flashes are very short. They're on the order of just 1 or 2 video frames. So they're very difficult to detect with the naked eye. They're also rather faint, having magnitudes between 7 and 10. And this corresponds to masses on the order of tens of grams to hundreds of grams. And we estimate crater sizes, crater diameters for these guys just to be 2 to 3 meters. So those are 4 typical examples. And now to the big one. So on March 17th of 2013 at 3:50:54 UTC, we detected the largest and brightest impact in our observing program history. So it's also the longest impact, lasting over a second. So I don't even need to put a box around this one. You can pick it out fairly easily, and you could have seen it with the naked eye. Now, the rest of my talk is going to focus on how we determine the peak R magnitude, the impactor mass, and meteor shower association for this impact. All right, so that brings me to the magnitude. Lunar impact flashes, the photometry for them is performed using comparison stars seen near the limb during our observations. So on this slide, I'm showing you kind of a blow-up of that impact flash. And then the top graphic shows the signal. So this flash was so bright that it saturated our cameras. You can kind of see on the top graphic the signal is clipped. We wanted to correct for this and find kind of a true magnitude. So we did that by fitting a 2D elliptical Gaussian to the unsaturated wings. And you can see that in the bottom graphic. So you can see the fit and then a kind of the top of the signal stump in red. Now this fit yielded a peak R magnitude of 3.1 plus or minus 0.4 magnitudes, and a corresponding luminous energy of 4.8 times 10 to the 6 joules. Okay, on to the energy, and that brings me to luminous efficiency. So luminous efficiency relates how much of the impactor's kinetic energy is converted to luminous energy in our camera passband. So this luminous efficiency is a rather uncertain quantity. So I've kind of just picked two here as representative. So in this table, the left panel, I've chosen a luminous efficiency of 2 times 10 to the negative 4. And on the right panel, I've chosen a velocity-dependent luminous efficiency of 1.7 times 10 to the minus 3. And that value is determined from an earlier study we did on lunar impacts and luminous efficiency. So using these two different luminous efficiencies, we calculated the luminous energy, the kinetic energy of the impactor, and the impactor mass. And so I'm kind of showing an average value and then a range of values based on the error in the magnitude calculation. So you can see, depending on my assumption of luminous efficiency, it matters a lot. So you get an order of magnitude difference in the kinetic energy and the impactor mass depending on the luminous efficiency we choose. So you see, we got an impactor mass of either 8 kilograms to 72 kilograms. And you might notice that I've assumed a velocity of 25.6 kilometers per second. So why have I done that? Basically, the night of our impact flash, we detected 19 multi-station fireballs over the skies of southern Ontario and the southern United States. So on the left, you see a map, and then the meteor camera locations are pinpointed, and on the right, just some example fireballs from that night. We wanted to characterize those 19 fireballs. So on the graphic on the left, we're plotting up the fireball radiant. So it's declination versus right ascension. And those are color-coded by speed. So the more red, the faster it is. And we see kind of a tight cluster of 5 that I've circled in pink. Now, plotting up the orbits of that cluster of 5, we see very similar orbital elements. And so I kind of listed those average orbital elements here. So we believe that this cluster of 5 kind of belongs to the same meteoroid stream. That stream has a radiant centered at 184.1, 4.4, and travels at an average velocity of 25.6 kilometers per second. So we searched the literature to see if we could find a match to our RA, dex, velocity, and orbital elements to see if we could find kind of a meteor shower already in existence. And we found 2 fairly good candidates, both in the Virginid complex. The first being the Northern March Virginids, or NVI, and the second being the Eta Virginids, or EVI. So both of these are fairly good candidates. And so what we may have seen on March 17th is an outburst of an already established meteor shower. So I'll also kind of point out here that the Tisserand parameter was greater than 3, and that indicates an asteroidal body, which will be pertinent to our assumptions regarding the density later. All right, so we wanted to further convince ourselves that the March 17th impact flash was related to the fireball outburst. So we wanted to determine if the Virginia radiant, or the radiant of our cluster, was visible from the flash location. So to determine the location, we used ArcMap, which is part of the ArcGIS 10 suite, to georeference the lunar impact video, both at the time of the peak brightness and at a time 10 frames after the peak. So we georeferenced the video 3 separate times and got 3 different locations, both for the peak brightness shown in red and kind of the late impact shown in green. So the late impact, the signal was quite a bit smaller, and so the center was easier to pinpoint. So in averaging the late impact location, we get an average location of 20.599 degrees north, 23.922 degrees west. And we wanted to, furthermore, plot a subradiant point on the moon, just to see the portion of the moon that was visible to the radiant. And basically our entire field of view was visible to the radiant that evening. And the impact flash falls well within the zone of visibility. Furthermore, the radiant from the impact flash location was only 34 degrees from the zenith. So we've assumed that the impact flash is caused by a virginid meteoroid traveling at 25.6 kilometers per second. That's the same speed as the meteors that we detected in Earth's atmosphere. And we've also assumed that it impacted at 34 degrees from vertical, according to the shower radiant. So next, we wanted to get a good idea of how big the crater might have been. So we looked at 2 models, Gulf and Holzapfel. So Gulf on the top, Holzapfel on the bottom. And again,
1 minute, Danielle.
All right, thanks. And again, we looked at 2 different luminous efficiencies and therefore 2 different kinetic energies. So on the left and the right, once again. We also made assumptions about the projectile density and the target density, whether it was, asteroidal or rocky, or we're going into regulus or hard soil or soft rock. And kind of combining different assumptions yielded crater diameters between 9 and 23 meters. And I feel actually the velocity-dependent luminous efficiency on the right-hand side may be a better assumption to make. So just looking at the right panel of these tables, I would say that the crater diameter is between just 9 and 12 meters. So that brings me to my summary. So the brightest impact flash of our 7-year observing program we saw on the 17th of March this year. And this meteoroid may have been part of a stream of large particles encountered by the Earth and Moon associated with the Virginia meteoroid complex. And that's as evidenced by a cluster of fireballs in the Earth's atmosphere. Using various assumptions, I've kind of just put forth a summary of parameters regarding the impact flash and the impactor and the crater. And so with that, I'll just open it up to questions.
Great, fantastic. We have one question from Jen Heldman, who says, have you done an assessment of possible hazards to humans during lunar surface exploration from meteoroid impacts? And can you discuss your participation, if any, with the LADEE mission to monitor impacts during LADEE operations?
Well, I know we'll definitely be observing during LADEE. I guess I don't remember the first part of the question. Oh,
an assessment of possible hazard to humans, yeah.
I don't know that I've personally done so, no.
Is there anyone
sure.
in...
I actually have Rob Suggs here who can address the human hazard.
Yeah, hi Jen. Yeah, we started this program for Constellation for exactly that reason. We got very far into the observing, obviously, but we needed to do modeling of the ejecta because we think that's the primary risk is from the ejecta. There's not much you can do about being hit by an object this size, but the ejecta is spread out quite a bit. Unfortunately, the program was canceled before we got the funding to do the ejecta modeling. So the full assessment has not been done, but that's where we were headed with it.
Dave Morrison has a question.
Very interesting result. Have you thought about the degree to which this is complementary the study of meteors in the Earth's atmosphere? Does it actually add to our knowledge of meteors, or are you just focusing on the specific question of what a hit does to the moon?
I mean, so we're part of the Meteoroid Environment Office, so we actually study meteoroids in as many ways as we possibly can. So, like in this particular instance, we're able to combine fireball data, so stuff that we're seeing in the atmosphere, and kind of get information about stuff that's also striking the moon that we might see as lunar impacts. So it's really kind of looking at it from multiple angles.
And I just had one quick question, and we just had a fantastic talk by Shane Thompson out at ASU about LROC and looking for new fresh craters. Have you given LROC, or have you gone through the LROC images to look for evidence of this new crater?
I did go online, but I didn't see, looking through images, but I didn't see any images of this particular region, at least posted online, after the March 17th date. So we did transmit our coordinates to LRO, and I don't know that they found any crater matching ours as of yet.
Okay, yeah, I'd be curious to see if they can go through a dedicated search and actually find that at some point. And also, Crystal from Pisces has